All right, so welcome. We are on part two. And the warm-up here, we do have a warm-up. Sweater relationships. If you remember from part one where we did Romeo and Juliet, this is obviously a play on sweeter relationships. But anyway, so what you have to do here is we're going to read through the warm-up, and then you're going to have to go to It's Learning and answer it. And there might be a couple other questions from this PowerPoint you have to answer. So make sure you do, and I will reveal the answers later. But here we go. You pull your sweater and shirt off together, and then pull them apart. You notice that they attract each other, a phenomenon called static. In everyday life. Okay, so that was timed weird. But explain the mechanism behind this attraction and suggest an experiment to test your explanation. So you pull them apart. The garments are obviously attracted to each other afterwards. But you have to figure out why that is and how can you prove it. Interesting. All right, moving on. Good luck with that. Okay, so we are on Unit 8 still, Electric Charge and Electric Force, Part 2, the charge, or Q to be specific. And what we have here over to the left is a picture of what is referred to as a Van de Graaff generator, I believe. At least that's what I was told it was. So the Van de Graaff generators are kind of neat. They no longer really are in existence. Like, you can find them as far as a teacher goes, but they are even before my time of even being a student. And if any of you say, wow, that was ancient history, yes, you failed. So Van de Graaff generators had like this belt in the middle of them that went from the ball down that would spin. There'd be like a motor here, and it would spin, and it would create the static electricity. And you would get these. These are obviously you wouldn't actually see these, but it would shock you if you tried to touch it, or if you put your hand on it and turned it on, then everybody touched it. Their hair would stand on end. And I asked the teacher once, why don't we have a Van de Graaff generator that works? Because the one I actually was there was very specifically disabled and then not thrown away. This teacher was like the most ridiculous pack rat. Like, she specifically disabled it as directed by the county, or the head of the science department, and then didn't throw it out. Like, I didn't get that. But anyway, the reason is if you get shocked, first off, you're inflicting pain on somebody. And why you would willingly inflict pain on students. Okay, so maybe I'm not the best person to answer why you wouldn't inflict pain on students, but you got the idea. But you'd shock somebody. Even if they liked it or they wanted to be shocked, it would hurt, right? The problem is it doesn't matter your size or gender or anything like that. Different people feel shocks differently. So a little shock that might not hurt, like someone 5'2" and 100 pounds soaking wet, might make someone who's like, at 6'8", 300 pounds fall down. It was qualitative. It wasn't really the measure of pain. How much you would feel would be different from person to person, and a bunch of people got really hurt, or their parents got really mad because they got hurt. So again, I have not seen a working Van de Graaff generator. Maybe someone else has them, but I promise you can probably find them on YouTube, just like everything else. But I digress. Let's move on. Okay, so we have the historical model of electric charge. And this is important to understand because the reason we have historical and current models is because we will be able to test things, and then those historical models wouldn't hold for that. So first there was what we called the fluid model of electric charge. And this was really kind of neat. Too much electric fluid in an object makes it positively charged, and too little makes it negatively charged. So that was kind of a neat idea. We had one that seems fairly similar to what we believe now, which is the particle model of electric charge. And this was an electric charge is carried by microscopic particles. Removing or adding these particles to an object changes the charge of the object. All right, so this would be your second part that you have to figure out on your own and answer. And basically, it's how could you test these models? And we've done some tests, right? You did see the balloon with the felt and the plastic. Hopefully, you remember doing that was a video of on part one. There was also a tape that you'd put two pieces of 8-inch tape on a table. You'd pull them each off, and then they would obviously repel. But something like that, something simple where you could explain why these models might not work, and you have to come up with that. And that's another part of your notes homework. All right, so our contemporary model, this is the one we use now. Two objects start as neutral. The total electrical charge of each is 0. That makes sense, okay. During rubbing, one object gains electrons and becomes negatively charged. And these are these free-floating electrons, normally from the valence shell, but they could become from below that. And the other object loses an equal, notice what that says, equal number of electrons. And with this, deficiency of electrons becomes positively charged. And that's what we believe now. So that's our current model that fits all this stuff. So right here, we have a neutral atom of carbon. You got 6 protons here. It's just designated by one picture. But then these electrons, notice this negative E. I wonder what that E stands for. Anyway, because the proton, the nucleus has a positive E? I wonder. Well, we'll get to that later. So these right here are these free-floating electrons, and they equal the number, so that would make it neutral, right? But one could be spun off. So on the sodium has 10 negative electrons and a nucleus with a charge of plus 11 electrons. So this negative obviously has been rubbed off, so to speak. That really sounds kind of weird, but you get the idea. And that is our current model of how the electric charge looks. And remember, this is a video. You can pause and rewind if I talk too fast. Okay, moving on. Right here, we got electric charge. So this is important to understand. Electric charge, the symbol is Q, or lowercase q or uppercase Q. It's usually a italicized one. I know that's not italicized there, deal. It's a property of objects that participate in electrostatic interactions. Okay, so charge is electrostatic interaction. That, we talked about that. That was part of our vocab. That's on part 1. Electric charge is quantized. I think I spelled that right. Quantized, which basically means you have a numerical value to it. You can only charge an object's charge by increments, not continuously. And that's important to understand. So if I take that I'm going to pay you to do something $5 an hour, and that's all I'm going to pay you. I'm not going to pay you in increments, only $5 an hour. And you want to end up getting $12 an hour. That's what you want. Well, that's not possible because I said I would only pay you $5 an hour. I'm not paying you, for half-hour work. It's either an hour or nothing or something like that. But it's has to be in that. The numbers you get of charge have to be in those increments. It doesn't just go 1, 1.1, 1.2, 1.3, 1.4. No. Increments. Electric charge is conserved. So that's important to understand. So what you have before is what you have after. It's kind of like what we talked about before. One loses, one gains. The unit for electric charge is a coulomb, which is done by the uppercase letter C. Not to be confused with the lowercase letter c, which would be light speed. Just so we know. We're running out of letters here, people. We got to uppercase some of them. The smallest increment of charge is that of 1 electron. There's that negative E, right? Because the E is technically the charge. So negative E equals negative 1.6 times 10 to the negative 19th coulombs. People, this is a tiny number. This is not millions. This is not billions. This is not even trillions or, of zeros. It's not quite a googolplex of zeros, but you get the idea, right? This is a tiny, tiny number. Hey. And that's another question. What is negative 19th called? I gave you a chart once. It was that one that looked like an hourglass. That's question number 3. So what is that electron? It's a very small charge, but everything, as it said before, as it says up here, has to be in increments of this. So you're not going to have negative 1.8 times 10 to the negative 19th coulombs. No, that's not how it works. Their charges have to be in increments of that. That's why you had that 10e. For the positive 10e for the protons or the nucleus of that carbon atom from that picture before. The magnitude of the charge is 1 electron, is sometimes called the elementary charge or elemental charge. So it's the base charge. It is that everything is every amount of charge has to be in an increment of that number. Moving on. Okay, tip. Notice how small the object of electron is. Even if we placed 1 billion electrons on an object, and let's not beat around the bush. 1 billion is a lot, people. If I had $1 billion, I wouldn't even be making this video. And if you had $1 billion, you wouldn't even be listening to this video. We wouldn't even know each other. But anyway, it will still have only negative 1.6 times 10 to the negative 10th coulombs of charge. That's still big, people. Typically, charges of objects through rubbing are about 10 times larger, but still are very small. 1 coulomb is a huge, huge charge. And you'll learn later in Coulomb's force that it creates a massive amount of force as you have a whole coulomb of charge. I figured it out once. I'm pretty sure I was right. I was young in my teaching career at Tyner. And we were doing this unit throughout the whole school. And everybody had to do something. And by the way, this is a digression. You can fast forward if you need to. Everyone had to do something about Titanic. And literally, this is what I was teaching on. So I took a coulomb of charge, right? And you'll figure out how to do this later with Coulomb's law. That's video, I think, number 4. And a coulomb of charge, and then I took it in increments of the Titanic as far as force goes. So a coulomb of charge that was 1 meter away from you was the equivalent of 23 Titanics dropping on your head. That's how much force it was. Now, it's very possible I was wrong. And if I am, or you can prove it, maybe I'll give you extra credit if you can show me that work. But it was a huge amount of force, and when I did it, it was an increment of 23 Titanics dropping on your head, which is... that would hurt, right? I had a picture of Wile E. Coyote because that's my thing. I digress. Moving on. All right. If you haven't noticed, I digress a lot. Practice makes perfect questions. So, idea of these questions or any of the questions we do. People, if you want notes to be effective for you, you have to interact with them. Even if that means yelling at the thing or telling me to shut up or stop talking or just simply putting in stupid numbers into a calculator that we're doing on the screen, do those things. Write down things. That's more. The more you interact with the notes, the more you interact with the lecture style, the more likely you are to actually retain the information in your brain and then maybe you can utilize it later. So when we get to these questions, I'm going to say pause. What you need to do is pause. Try to do the question. Even if you're wrong, who cares? Now, maybe I'm collecting these notes or not, but on some of these, if I don't see that you tried to do it and got it wrong because I haven't, I kind of doubt you'd get it perfectly right the first time, I might not even give you credit. I'm not saying make mistakes on purpose, but try these things on your own first. If you're wrong, just put an X through them or a line through them. Don't erase them, and then write what's correct next to it. That's how you learn. It's important, so do try this when I get done reading it. When an object gets charged by rubbing, where does the electric charge originate? A, it comes from the air surrounding the object. B, it is created by rubbing energy. C, the process of rubbing leads to a redistribution of charge, not the creation of charge. So you're going to take a guess which one, A, B, or C, and then you're going to defend your answer. Try to use your notes. If you can't figure it out from your notes, pause the video, rewind, and see where I talked about this. Okay, pause. Hey, I am playing pause. You have not hit pause. Okay, good, pause. All right, so hopefully you've taken your guess at this point, and the answer happens to be C. The process of rubbing leads to a redistribution of charge, not the creation of charge. As you rub, electric charge is lost by one object and gained by another object. Nothing is created. So, and I've said this before, human beings aren't capable of creating anything. All we do is reorganize stuff, so to speak, or we change its we don't actually create stuff. We just change the way it is. We are what we eat. That kind of thing. So there's nothing created. It doesn't come from the air per se. It doesn't come from rubbing. I don't even know what rubbing energy is. It's not anything. But so you're rubbing. You're redistributing that charge. You're taking from one atom, so to speak, and adding it to another. In a sense, you're taking those electrons and losing them. Okay. Lightning. Again, practice makes perfect. But I will admit, this one you kind of probably want to do with me a little bit. Maybe pause it, try to take a guess. But this one is a little bit weirdly, but it is kind of neat. Lightning. A cloud has a large positive charge. Assume that this is the only cloud in the sky over Earth, and that Earth is a good electrical conductor. Draw a sketch showing the electric charge distribution on Earth due to the cloud's electric charge. Explain why a person's hair might stand on end. Okay, so I didn't actually do this exactly the way it's supposed to. What I did is I drew the cloud, right? Here is my cloud, and that is with the distribution. So if the cloud is positively charged and the Earth is obviously negatively charged, because those are the kind of, that's the charge it would attract if it was positive. And then what would happen? Well, you would be standing on the ground, right? And the negative charge would flow through you. And what's the closest to the cloud? Probably your head. I mean, if your feet are close, that means you're doing a handstand, and we're not talking about that. But your head would be there, right? So these electrons would flow through your body up into your hair, and they would try to make your hair lift up, right? Because you've seen charge actually move stuff with the balloons or with the tape, right? And it would stick straight up towards the cloud. But now realize each piece of your hair has these negative charges in it. So they, of course, would separate. And that's kind of what it would look like. Mr. Cooper, why didn't you draw that? Because people, you don't even know how long that stupid drawing took me. Okay, since the cloud is positively charged, negative charge will be attracted toward it from the surface of Earth. They move into your body and then onto your hair. The force of attraction of the positive cloud on the negatively charged hair can make the hair stand on end. While the repulsive force between the strands, because they're all negative, like charges repel, spreads the hair out. There you go. All right, let's keep going. All right, so part 2, the charge Q. All right, so now we have electric current. Okay, pay attention, this is an important part. The magnitude of the physical quantity of electric current, which is I, in a wire equals the magnitude of electric charge Q that passes through a cross-section of the wire divided by the time interval delta T needed for that charge to pass. Again, this is the verbal equivalent of an equation, but it's not that complicated. Take a look at the parts. The magnitude, so the size, physical quantity number, so the size of the number of electric current, which is I, in a wire equals the size of the electric charge, which is Q, that passes through a cross-section. So you have this charge passing through this little section of wire divided by the time. And there you go. I, absolute value here, Q over delta T. That makes sense. Remember, I is current here. It is not moment of inertia. Now, the unit of current is the ampere, and we use the unit of current. So I is the symbol we use for it, and A are the units of it. We can't use A here because it's kind of like acceleration. People get too confused. Equivalent to 1 coulomb per second. A current of 1 amp, 1 ampere or amp, means that one current of charge passes through a cross section of the wire every second. The direction of the current is from higher potential to a lower potential. Therefore, it is in the direction that positive charges would move. So again, 1 coulomb per second, a current of 1 amp, means that 1 coulomb of charge passes through a cross section of the wire every second. Now, electric current. The SI units for electric current is a fundamental unit, like meters, seconds, things like that. The unit of electric charge, 1 coulomb, is defined in terms of the amp, which is 1 coulomb equals 1 amp times 1 second. Okay, quantitative exercise. This is one I want you to try on your own, and I want you to use your notes. And if your notes can't help you, pause. Go back in the video and find the notes that will help you answer this question. Each second, 1.0 times 10 to the 17th electrons pass from right to left, past a cross section of the wire connecting the two terminals of a battery. Determine the magnitude and direction of the electrical current in the wire. Now, read it, pause, try to do it on your own. Answer. Now, here we go. We know that current equals Q over delta T. We just learned this equation. So this is going to equal something over delta T, Q, which is negative E N. Huh? The heck is he talking about there? Think for a second. The unit of current, right here, 1 coulomb of charge passes through a cross-section of wire every second. This is your number of electrons. This is your charge of an electron. This is your N, your number of electrons. Remember? So 1 coulomb of charge passes through a cross section of wire every second. So I equals negative 1.6 times 10 to the negative 19th. Huh? Where'd that number come from? You don't remember that number? Really? Because if you look at this page of notes that you just took, and you look right there, that's where that number came from. That's your unit of charge. But you have a number of those charges that go through, correct? Which was that number. Remember from the problem? So this is many electrons. This is the charge of an electron, but you have that number of them. So Q is your charge. This is your charge. This is your elemental charge, and this is the number of them. That would give you your part. 1 second. Now this may sound stupid. Put the numbers in your calculator. Seriously, it may sound silly, but put them in there. Negative 1.6, in your calculator will look like this. Negative 1.6 E, negative 19. That's that EE button. You don't ever write times 10 and then the caret button. That always gets funky. 1.6 second button, and I think it's the comma, but it's the EE, but on your screen it shows E. So 1.6 E, negative 19 times 1 E, 17. Enter, divided by 1, although you can do that, and you get this. 1.6 times 10 to the negative 2 amps, or 1.6 milliamps. And I can't remember if I told you. Find out what the name of this number is. I did give you that sheet with prefixes shaped like a, what do you call it? Dinghy? A sandglass? Hourglass? It's your third question. But there's your answer. And we do things in milliamps a lot. That's what normal current is in, milliamps, so to speak. We don't deal with full-on amps. That's redonkulous. That's way too much. Moving on. Practice makes perfect question again. So again, you're going to try it on your own after I read it and see if you're right. A researcher is analyzing data from a higher energy particle collision. The result of that analysis gives a value of 8.8 times 10 to the negative 19th coulomb plus or minus 0.1 times 10 to the negative 19th coulomb for the charge of one of the emitted particles. Should the researcher accept the value? Justify your answer. Yes, perfectly acceptable. No, because the value is much bigger than the elemental charge. No, because the value is not an integer of the multiple of the elemental charge. No, because the uncertainty is more than 1% of the value. Take a guess. Figure it out. Take a guess why. If you don't know, go back through the notes. The answer is no. It's not a value of the elemental charge. Since elemental charge is the smallest charge possible, all other charges have to be multiples of that value. That was that 1.6 times 10 to the negative 19th. That ain't no integer of it. If you divide it by that, you're not going to get some nice even number. All right, folks, that is the best I got for today. Feel free to look it over, rewind, make sure you answer those questions that are on It's Learning for this particular set of notes. And as always, obviously, if you took these notes at home, you will have to turn them in for Mr. Cooper's class. Have a good day.